Okay, so in this video, we're going to really start talking about what is temperature, because temperature really affects the partition function and the states that our molecules exist in. And so it's going to be important that we spend some time and really define what temperature really means. And in the process, we're going to learn a little bit more about math and some of the reasons why we use different sorts of functions and calculations. Okay, so where are we going? Really, we're trying to regain some perspective. Our overall goal of our semester is to predict the properties of bulk materials from the properties of individual molecules. If you haven't gathered yet, this is hard to do. And our general approach to this is that we eliminate variables from our system until we have a model that we can understand. Then we apply the principles determined from the simple system to more complex systems, and we see if our model is still valid. And so our basic system is an ideal gas. And we talked about ideal gases in general chemistry, but it turns out that in physical chemistry, we rely on the approximations made in the ideal gas approximation a ton. Okay, so what is temperature? No, what is it? At this point, we've determined that temperature is an intrinsic property of the system. We've defined it as the average kinetic energy. We know that at different temperatures, the Maxwell-Boltzmann distribution takes different shapes. We also know that temperature is inherently tied to the energy of the individual molecules and thus the energy of the system. But these are all observations and sort of vague definitions, and not really a mathematical or rigorous sort of definition of temperature. So, to really get into this view of temperature, we're going to work through a derivation. So, physical chemists use derivations to start with our simple system, this thing that we create in our head, and we work through the math of the simple system to see if it can give us a relationship or a property or something or a function that we can use and apply to other things. So in our derivation, we first have to define our system and our surroundings. And so what we have is we have a sealed container. We have our sealed container, this pink box in the middle. This is our system. Our system contains 3 molecules. And these molecules inside of our system, they can move around. They're gases, so they're pretty far apart. And we're going to assume they're ideal gases, and so that means that they don't interact with each other. They can bounce off of each other. They can bounce off the walls. Surrounding the system is a reservoir. So this is the surroundings, but we're going to really control our surroundings. So maybe it's the room that our experiment is in, or maybe we put our experiment inside of a box and our surroundings is that sealed container around our system. The molecules in the reservoir or the surroundings, these molecules cannot move between the system and the surroundings. The molecules on the outside are on the outside, the molecules on the inside are on the inside. But energy can move between the systems and the surroundings. And what we're going to say is that the number of microstates of the surroundings or the reservoir are much greater than those of the sample. So notice that we're giving the sample the symbol E, the reservoir E sub R, and their corresponding microstates. And we're also going to say that the first law of thermodynamics holds, which means that energy must be conserved. So our energy of our system plus our energy of our reservoir is equal to our total energy, and our total energy is much greater than the energy inside of the system. So this is our system. We're all okay. So these are our starting definitions of the conditions that we're working on. So the size of the ensemble, or the number of microstates, is a function of the energy of the system. If the energy of the reservoir increases, then the energy of the system must decrease by the same amount, because we know that our energy is conserved. So our system plus our surroundings equals our total. There's no universe in this example. And so if we think about our microstates as a function of energy, we can get our total microstates is going to be the sum of the microstates of the system times the microstates of the reservoir, summed over all possible energies. If your brain's not hurting right now thinking about how big that number is, it should be. So now, let's pick a single microstate of the system. So how do I like to think about this? I like to say, okay, these three molecules in our system, they don't get to move. They must have identical energies. They must be in these exact positions. And now we want to say the probability of this state occurring is the fraction of the number of microstates within our system divided by the total number of microstates. But our problem's a bit more complicated than just those three molecules. In reality, we want to allow all the molecules to move and determine the probability of these three molecules in the system being in these same conditions. And so what we are going to do is we are going to set our system, and we're going to allow the reservoir to move around instead. And so the probability becomes the number of possible microstates in our reservoir divided by our total number of microstates, because we're going to pick and say that our system has to match these three, but our reservoir can move. Okay, so we can define our probability by really just looking at our reservoir when we have a small system. We could even begin to count the number of possible microstates if we just think about XYZ positioning of these molecules. Or I have a two-dimensional box and XY positioning. But when we start thinking about realistic number of molecules and all of the possible variables that exist in a chemical system, working with omega gets really hard because the numbers get really big. And so what we can do is we can use the Boltzmann entropy to help us out. So remember that entropy defined by Boltzmann is really just a count of these microstates, but we're going to count with this natural log, and so that natural log helps us get rid of these giant numbers. So now that we put our function in terms of the natural log, we can employ what's known as a Taylor series expansion, make the math more doable, and manipulate some things algebraically, do some calc too, and eventually we arrive at this expression where the temperature is defined as the partial derivative of the energy divided by the entropy, while holding the volume and the number of moles of sample constant. Okay, math interlude. What is this partial derivative? Temperature. So the temperature is the derivative of the energy with respect to the entropy, but we're going to make sure to keep the volume and the number of moles constant. Okay, so now, great, this is an expression, and right now it doesn't mean much, and right now it's a definition, not an equals, so using it's going to be really hard. So let's talk about what this means. Okay, so this is the first time this semester that we've seen partial derivatives. If I have a function, let's say my function is a function of x comma y, and I'm just going to pick something. I have 4xy plus 3x squared plus 6y cubed. The partial derivative of my function with respect to x, meaning that we are going to hold y constant, means that I am going to take the derivative of with this equation, just treating x as a variable. If I encounter a y, it behaves just like a number because I'm holding it constant. And so the derivative of 4xy with respect to x is going to be 4y, following our normal derivative rules, plus the derivative of 3x squared. There's no y here to hold constant, so I get to take the derivative just like I would in single variable calculus. Gives me 6x plus 6y cubed. There's no x here, and so this is a constant when we're taking the derivative with respect to x. And so the derivative of constant is 0. Okay, so in reality, partial derivatives are really just like normal derivatives. We just have, it's what we use when we have more than one variable. Okay, so now I'm going to go back and we're going to look at this definition of temperature. So what this means is that if we were to make a graph of the energy versus the entropy, the temperature is defined as the slope of this line at a particular point. And so our temperature is equal to the slope. Because remember that the first derivative of a graph is the slope of that graph at that point. So, okay, does this mean anything to us yet? Well, temperature is really, this should help us realize that temperature is really defined as the relationship the amount of change that is happening to the energy when the entropy changes. It's that slope between how quickly when we add energy, how quickly the number of microstates change, or when we add microstates, how quickly does the energy change? Okay, so now try this. There are no problems. This is a definition because we're going to really build upon temperature from here. We're going to use it. We're going to think about how it influences the microstates and the population of these microstates by molecules in our system.